what the directions are on these. I want to do this one here. I think this is question 17 or 18. And it tells us at the beginning that these two triangles are similar. Based on the information that is here, you have absolutely no idea whether they're similar or not. So the directions have to tell us that these two triangles are similar. Okay? I think, and I view these things, and I'm not saying the way I do it is right or wrong. I just think it's easier for me. I like to separate the triangles. So I'm going to redraw this top triangle with the 14 and the x plus 3 there. And then we'll look at the bottom one, or the overall one. And then, so what would I be able to call that distance, or refer to as that distance? Based on this information over here, x plus 14. Okay? That's x plus 14, and like this transferred over as x plus 20. All right. Now, you could kind of blindly approach this, and I think most people would probably say, hey, the 14 is going to go with the x plus 14, and the x plus 3 is going to go with the x plus 20. Would you all agree with that? And the reason that happens, and that you can do that, I think is like a sketchy type process. I would not be comfortable doing that. Because remember I said largest has to go with largest, smallest with smallest, right? Do you know which one of these is the largest? Do you know which one of these is the largest? Does that kind of make sense? Because they're algebraic expressions in 3 of the 4, you don't know what's the largest segment, what's the smallest segment. So I don't think that process is really available to us. Now, you could make the argument that, well, if they said these are similar, that angle and that angle have to match up because it's shared by both triangles. Okay? If they're similar, that one there and that one there match up. Okay, does that make sense? So then you could say, okay, well, 14 is between the angle that has 1 mark and 2 marks, and so is x plus 14, so they have to match up. And then what's left over matches up or corresponds. I like to do this. I like to introduce some letters here. And I like to say, because of these angles, I can say triangle ABC is similar to triangle. If I go A to B to C, I got to go A, D, E. And this then is going to guarantee, when I write these ratios, it's going to guarantee that I link the appropriate sides with one another. Does that kind of make sense to everybody? All right. I've mentioned several times that that's kind of the fail-safe technique for making sure you get the right proportion. So AB was 14. AD ends up being x plus 14. BC is x plus 3. And DE is x plus 20. Okay? They were okay with that? And right there, if you write that, you have demonstrated that you 100% know the geometry. Okay? But on the end of course exam, how do they ask for you to demonstrate that you know the geometry? They ask you to type in what is x, what is the solution for x, right? Okay? So now, and this is something that I struggle with as a teacher trying to get students to recognize and realize, is that once you've taken algebra, whatever level it is, algebra 1, everything after algebra 1, when you start doing math problems, there might be algebra 1 material that shows up that you have to understand how to address it. After you're taking algebra 2, and then you're in trig or you're in college algebra or calculus, there's going to be algebra 1 and algebra 2 information that shows up that you're just going to have to know how to deal with it. Okay? So here, when I get this, I get some algebra 1 stuff that shows up that I have to be comfortable with in how I deal with it. If I cross multiply those two things, you should get 14x plus, 280? And when I cross multiply my means, I don't know why this keeps doing this. There we go. When I cross multiply my means, that's a binomial times a binomial, right? So I got a FOIL. So there's some algebra there that maybe we need to jog our memory with. So x times x gives me x squared. X times 3 gives me 3x. And then 14 times x gives me 14x. And then 14 times 3 gives me 42. Okay? And this is the algebra component that I said needs to kick in. When I have a term, my largest largest exponent is a power of 2, and eventually you'll find out if it's a power of 3, power of 4, power of 5. You will do the same thing. That's what Algebra 2 and college algebra teach you of how to do. Okay? But you're going to factor. Okay? So if I want to factor things, what do I got to get everything equal to? 0. So I'm subtract 14x from both sides. And I'll subtract 280 from both sides. So it's going to be 0 on the left, an x squared. Those went away, so it gives me a plus 3x. And this ends up being negative 238. Okay? Now remember what we're trying to do. What relationship between numbers am I looking for that are going to generate that number right there? The two numbers, the two factors have to do what together to get 238? Multiply. Okay? And they have to do what to get 3x? They have to add, right? Okay? Now, when it's negative here, when that negative 238, that means if they're going to multiply together to give me a negative, they both have to be, or one has to be positive, one has to be negative, right? And they add up to 3. 3 is a pretty small number, correct? 3 is pretty close to 0, correct? Okay? Now, and this is the process that I go through when I don't know my factors for 238. I don't want to sit here and go, 1 times 238, does that add up to 3? 2 times 1, 69, does that add up to 3? Okay, I don't want to be or have to do that every single set of factors. Okay, is everyone on the same page with that? Okay, so what I like to do, if these numbers are close to one another, and it's a logical thing, if this number was 0, x, one of the two numbers that multiply together give me negative 238 have to be the same number, but opposite signs. That makes sense? Okay. And if I'm going to find a number that multiplies 2 times by itself to get 238, by definition, that is what a square root is. Does that make sense? Okay. So what I'm going to do is give myself kind of a jump start on how to find these factors. So I'm going to take my calculator. I'm going to take 238, and I'll take the square root of it. And that gives me that number right there. Okay, so by definition of what a square root is, that means if I take 15.427248 and multiply it by itself 2 times, so 15.427 times 15.427, it's going to give me 238, right? If one of those numbers was positive, one of those was negative, it would give me 0x, right? Want to add them together? Okay. But this case is giving me a 3x, a number that's relatively small compared to 0. So what I do to check to find out what my factor is I take the 238 and I start dividing it by whole numbers that are close to 15. Okay? So I'm just going to try 15 as my starting point. My hopes are that we know that 238 is not going to divide by 15, right? How do I know that? 238 ends in an 8, right? 15 ends in a 5, right? So if they're going to be divisible, doesn't the 238 have to end in either a 5 or a 0? And in this case, it doesn't. So I know it's not going to. I know it's going to give me a number that is not divisible by 15. Okay? So what I'm going to do then, we'll go 238, and now you got a choice, and it doesn't matter. You can either go up or you can go down. So I'm going to choose a number that is bigger or smaller than 15, the next integer. So if you want to go up, it would be 16, right? So divide by 16, and it doesn't give me a whole number. So I'm going to go up again by 1. So 238 divided by 17 give you a whole number. So what's that tell me? It tells me that 238 is equivalent to 17 times 14. Does that make sense? Are 17 and 14 3 units away from one another? And if one of them is positive, one of them is negative, we've got what we need here. So my two numbers that we're looking for are 17 and 14. If I want them to be a positive 13, the 14's got to be negative, right? So we're going to rewrite this as x minus 14, x plus 17. Someone in the last class said, okay, I didn't do that, but I just took my calculator, took 238, started dividing by 2, divided by 3, divided by 4, divided by 5, until I got two numbers that were 3 units apart from one another. And that's fine, that works. It's time consuming. And what happens if I give you, like, instead of 238, I give you, like, 2,380? Okay? So you've got much larger composite values. You want a better starting point than 2, right? Does that make sense? Okay? So this means x minus 14 is going to be 0, or x plus 17 is going to be 0, right? So x is 14, x is negative 17. When you're working on these problems, and it's all dependent on the distances and the expressions that they give you, they're going to tell you, if necessary, type both answers in separated by a comma. Okay? So that tells me that one of these might work, both of them might work, neither of them might work. There might be no solution here. I have to go back up to my problem and see which ones are capable of being used. We said x was 14 and x was negative 17. Those are only two answers, right? If I put 14 in, that distance becomes 17, right? This one becomes 28. This one becomes 34. Are all those red numbers legal distances based on how we define a distance? Distances have to be greater than 0, right? All of those are that. So 14 works. 14 is a solution. Okay? Now, just because 14 is a solution, this is all mathematics from here on out. When you get multiple answers, just because 14 works doesn't automatically mean the other one doesn't work. Okay? You have to check, especially if there's context to the problems, a story, a picture, something like that. I'm putting in negative 17. What's negative 17 plus 3? Negative 14, right? And right away I see that I can't have a distance of negative 14, so negative 17, we wipe it away. It's not a solution. Okay, you get to, have you guys heard the phrase extraneous solution before? Okay, root word for extraneous is extra, right? Okay, when we get into algebra 2, you probably talk about it a little bit more detail. Essentially, through the algebra that we conduct in this problem, that number is generated, but it is not a solution. Okay, kind of talk about that here, maybe in a graph for you. Another thing to look at, so when I'm done, let's compare that 14 to that 28. What do you get? 14 divided by 28. The half, right? If I take 17 divided by 34, is that a half? And that 1 to 2 equaling 1 to 2 tells me right away that I know that 14 was the right answer. If I don't get that 1 to 2 each time, I know my algebra is wrong. Go back through, look at my factoring, that kind of stuff. I think this might be appropriate to have this discussion real quick. Let me write this equation. 14 over x plus, what was it, x plus 4? X plus 14. X plus 3 over x plus 20. So if we were to graph these things, okay, these are called rational equations, okay? So all I did is I graphed the left-hand side of this ratio, or this proportion, and then I graphed the right-hand side, okay? You get to college algebra, algebra 2, you talk about these a little bit. It's a rational equation, okay? That's the green one. That's the red one, okay? Remember, when we're trying to solve equations, and you did this with systems back in Algebra 1, the solution to every equation is where the graph of the left-hand side of your equation intersects the graph of the right-hand side of your equation, and it's the x value of their intersection. So if I look at these two things, okay, and I start to look and see over here where they intersect, okay, let's see here if we can do it this way. Intersect that one with that one. Do I have these typed in right? Aha, thank you. That's a 2, 0. That's better. So now you see that at this point here, you see the red curve and the green curve coming together, right? They're merging together. They merge together right there at this point of 14, okay? Is that the x value that we found as an answer? All right with everybody? So you get, and I've asked this before, you're getting ready to take the ACT. Let's say we're on the ACT, and I've got my TI 83 or 84. I've got this calculator right here, okay? And I've got an option. I've come up across this rational equation or this proportion, and I've got an option. Do I want to go through all the work that we just went through with factoring and all that kind of stuff, or do I want to type in the left-hand side into my calculator, type in the right-hand side of my calculator, and go see where they cross? Wouldn't that be much more efficient and quicker? And that's math, guys. What we just did right here, this stuff, it's math. Yes, it's fine, but it's more arithmetic, okay? But understanding what these solutions really mean to us and alternative ways of finding them, that's mathematics, okay? So like I said, I think that was question maybe 18. I think this question here is maybe question 8, might be 6 or 7 in that vicinity. This does not tell me whether the triangles were similar or not, okay? Maybe it does. I think it does tell me these triangles are similar, but I don't have the ability because one of them is showing, well, let me phrase this way. Do you know, looking at this picture, what that number should relate to in the other triangle? Or what value or expression or segment? If these two triangles are similar, that 39 should compare to what? What should I put in this denominator? X plus X, Y. Okay, so hypotenuse to hypotenuse, right? Now, why do I match hypotenuse to hypotenuse? Okay, good. So the hypotenuse in right triangle is always going to be the biggest side, right? And we've talked about if these things are going to be similar, the largest side has to match up to the largest side, smallest to smallest. So that tells you to match those two up. So then by default, these other two need to match up, right? Okay. Here's my overall complaint with this question. I think most people would do it this way. You don't know what that distance is, and you don't know what that distance is. So you don't necessarily know whether 2x minus 4 matches up with x plus, or 2x minus 4 matches up to 24, or it matches up to that vertical green distance, right? But, because we don't know that green distance, I think logically it makes sense to just compare 2x minus 4 to 24. This is a nastier kind of problem here because of the multiplication that implies, or that is necessary. Would anybody reduce this stuff over? Do you guys see that there's a reduction that can be done right there? Does every single value up there have a 2 in it? So if you wanted to, you could rewrite that as x minus 2 over 12, and that will make your multiplication a little bit easier. I'm going to avoid that because I want to demonstrate and remind you of a process that you go through with factoring, but you could divide right here everything by 2, and it'll make things a little bit easier in cross multiply. If I don't, if I cross multiply those two things there, I get 936, I believe. Just double check real quick. 39 times 24, 936. Okay. When I distribute here, x times 2x, 2x squared. X times negative 4 is negative 4x. 6 times 2x is 12x. So negative 4x plus 12x is 8x, right? And then 6 times negative 4 is negative 24. Got a power of 2 here. I'm going to factor, so I got to get things equal to 0. And at that stage, these are the types of questions that I worry about on the end of course exam, because you're going to be judged off of your algebra skills to tell me whether you knew to write those proportions correctly. Does that make sense? Okay, and my fear is that, it's been a year or so since we've done this and demonstrated on that test previously that we can factor these things. Does anybody remember what we do in this situation when this number right here is not a 1, when the coefficient of x squared is not a 1? What is the first thing you try to do? Okay, so divide everything by 2. So here's my question. Let's look at just something graphically real quick. If I take like 2x squared plus 8x minus 960, and let's do it this way. Let's write it as y equals that. Let me just change the scale here real quick. X-axis. Let's go. So there's my parabola that we're working with, right? Does that make sense? Okay. If I take and write 2 times y equals 2 times x squared plus 8x minus 960. It's not going to do it. That stinks. Why won't it put the 2 here? Two times. There we go. All right, so this equation, let me see if I can show it to you in the input format. Red equation is what we came up with by hand, right? Black equation, all I did is I took every single term and multiplied it by 2, right? Are the graphs the same thing? That make sense? What if I want to multiply this thing by 11.2 and 11.2? Different equations algebraically, but do they provide us the same thing? So what if I, instead of multiplying everything by 2, I multiplied everything by 0.5? What's multiplying by 0.5 the same as in regards to division? Dividing by 2, right? Okay. So I'm seeing here, I don't like that format that I just put in. So here, the input, okay, was a 0.5 in front of this and a 0.5 in front of this. Okay, but when I ask it to actually multiply it together, it gives me back this red stuff, right? So what I'm trying to show you here is that we are allowed, and you worked with this in systems equation last year. Remember taking any system that you ever worked with, and you're allowed to multiply either the first equation or the second equation by any number you want to? If you multiply by a fraction, that's dividing any equation by anything you want to. And the reason we can do that is because you're doing the same thing to both sides. So you don't change the equation. So I want to see, does everything divide by 2? And this gets overlooked sometimes because of what the quotient ends up being. But I'm even dividing the 0 by 2. Because I've got to do it to both sides. So does that give me 0 is equal to x squared plus 4x minus 480? Does that make sense? Okay. So now it's in a format that maybe we're more accustomed and more comfortable kind of factoring. Okay. I know 20 squared is 400. 20 squared is 400. So that kind of puts me at a starting point to get this 480. Does that make sense? So we'll take 20 times 24, because 2 times 24 gives me 48, right? So 20 times 24 is going to give me 480. And doesn't the x minus 20 and x plus 24 have to work out that way? So give me a positive 4 when I add them together. Does that make sense, everybody? So then when I solve that, x minus 20 equals 0, x plus 24 equals 0, x equals 20, x equals negative 24. Got to check my answers. If I plug in negative 24, it gives me negative distances, right? So x is 20 is the only one that works. Okay. You guys have some peers right now that are in geometry, and they're also taking algebra 2. Okay. I think Keaton Lyles is doing that, and Alex Gerton. Okay. Talk to those two and ask them how important is factoring for algebra 2. Okay. And they're going to tell you you do it every single day. All right. So it's going to be much easier when you get there if you take the time to learn how to do this and just kind of jog that memory from last year. Okay. And if you're thinking, well, I'm not going to do that then, I'm going to go to integrated 3. Integrated 3 is algebra 2. They're the same course. Okay. So factoring becomes a very, very, very critical thing for us. All right. So keep working on that assignment do this evening. But those were the ones, because of the algebra, that I was most concerned about. Okay. I want to introduce, we're not going to get through all of this, but introduce section 7.4 to you. And we effectively kind of introduced that the other day with this question. So I'm going to just pull this and cut and paste it and copy. All right, so you guys remember doing this question the other day with that worksheet that I gave you? And we talked about, okay, when I draw CD, and then this is this overall triangle here is a right triangle, yes? Okay, and when I draw CD from the right angle to the opposite side, that distance right there is, by definition, from chapter 4, you're going from a vertex perpendicular to the opposite side. That is an altitude. Is it okay with everybody? When you're in a right triangle and you draw the altitude that goes through the inside of the triangle. Okay, that's only one of our 3 altitudes, but that's the only one that goes through the inside of our triangle. It segments our overall triangle into 2 smaller ones, right? So these 2 smaller right triangles, and we've got this overall triangle. What this question talked about is the fact that this segment, CD, this altitude being drawn, generates 3 triangles that are all similar to one another, meaning their sides are proportional. And we went through the discussion of how to get these 2 triangles identified. So this is looking at the overall one, and let me color ACD, which would be this green one. So we're looking at the overall one and this green one. And we said, okay, well, they both have angle A in them. So we put angle A first. Okay? They both have a right angle. Okay? In the overall one, C was our right angle. In the green one, D is our right angle. Does that make sense? So I made sure that those were matched up in their position. And then the remaining letters, B and C, were the third letters that make either the overall triangle or the third letter that makes the green triangle. So they had to match up, and they were the third angles that were congruent. From that, we generated these ratios and knew that proportion was true. What I want to look at here, guys, and we could do this, and we will do this with all three of these relationships. But what I want you guys to look at is when let's wipe one of these out. Let's wipe out let's get rid of this ratio here. If I look at these two, so this is the first one and the last one. What do you recognize about that number right there, or distance, and that distance right there? They're the same. Okay? We'll go down to the next set. If we wipe away it's terrible. If we wipe away that one there, what do you recognize about that distance and that distance? They're the same, right? BC and CB, they're the same. And in the last one, I think maybe you can probably see what's going on here. And it's actually, they're written in a different order, but we see, is that there the same as that one? Now to get them in the right kind of comparison as everything else here, can I take this fraction and write it over here instead? Does that make sense? And if that's not there, then those two things are the same. So are we seeing that those positions that I highlighted are circled? What are those called in a proportion? We've got our extremes and we've got our... You remember what those positions are called? One's in the middle. Those two, those two, those two. You guys remember calling those means? Okay. Every single time we look at these three triangles that are similar, okay, from drawing this altitude, we are always going to get in each comparison, or no matter which set of triangles we compare, the smaller two ones together, or either the small ones compared to the biggest, you're always going to get a ratio in which its denominator is the numerator of another ratio. Does that make sense? AC is the denominator here. It becomes the numerator in this comparison here. CB and CB. CD and CD. Okay? Now, you might be thinking, well, yeah, what does that mean? Well, who cares? They're the same, so what, right? Come back up here and look at this picture. Let's look at what CD is. Because CD, and was in this last one, okay, in the means location, we get CD. Well, CD was an altitude, right? Okay. Let's look at this one here. Okay, this middle one. It's BC. Anybody remember what BC is for the overall biggest triangle up there? BC goes from a vertex perpendicular to the opposite side. What's that blue segment called? Well, what's the red segment called? Because it does the same thing, doesn't it? The red segment goes from a vertex perpendicular to the opposite side. We call the red one an altitude, right? What's the blue one? Altitude. CB, altitude. Or CD is an altitude. CB is an altitude. What's AC? What's that distance right there, which is those two? Is that also an altitude? Okay. So what we find out here is that when we take a right triangle and we draw the red altitude, okay, it is going to be what we call a geometric mean. And all that means is that distance, CD, goes in the means position, okay, in both ratios, okay? Same thing happens with the blue segment, which is also an altitude. Same thing with the green one, or about the green and the purple one, okay? So that's what this section is getting to and is going to talk about in a little bit more of a kind of detailed, kind of slow process, okay? And how we get those ratios to show up. Because I'm going to give you a bunch of problems that have these right triangles with that altitude drawn in it. I do not want you to have to do what you did on that worksheet to get the answer, okay? Because that's going to be messy. It's going to take time. It's going to be time consuming. So we're going to use these properties, these theorems, that automatically generate those ratios that were sitting there. Okay, so we talked the other day that those are the means, right? X and Y. Those are the things in the mean. We're calling means position. A and B would be your extremes, right? Okay. When, get rid of this. Actually, let's do this. Okay. When the objects in the means position are identical. Okay, so right there, X is the same thing. Okay, so it says if A, B, and X are positive and you have this proportion, we refer to it as X because it's in the mean position. We call them a means. But because they're the same thing, we call them a geometric mean. Okay, a lot of times when we're talking about multiplying things in mathematics, for some reason we call them geometric. Okay, you guys remember doing sequences last year? Like if I say 2, 4, 6, 8, you know what the next number is, right? And you guys can write formulas for doing that. So 2, 4, 6, 8, next number is probably 10, right? You guys remember those called arithmetic sequences? And arithmetic kind of meant or referred to adding or a common difference. Okay? You guys remember doing things like 1, and then the next number is 1/2, and the next one was 1/4, and the next one was 1/8, and then 1/16, 1/32, 1/64. And that was multiplying each term by 1/2, right? Multiplying by the same thing a lot of times is referred to as geometric. You called those geometric sequences last year. Okay? So, same type of vocabulary here referring to multiplying by same amounts. Okay? So X is called the geometric mean between A and B. All right? Why do we have to talk about that? When we're going to see a theorem here, it's actually a corollary. I'll skip some stuff that we already kind of know, that uses that phrase. So if I introduce this without discussing what a geometric mean is, you're going to have absolutely no idea what we're talking about, right? There's a lot of vocabulary in here. Altitude, hypothesis, hypotenuse, geometric mean. There's a lot of stuff there that if we don't know any one of them, we're not going to be able to apply this theorem and use it. Okay? It says when the altitude is drawn to the hypotenuse of a right triangle. So when they say of a right triangle here, and this is kind of confusing because of the fact that this picture is kind of a picture that is drawn after you drew that segment. So if I start with that purple triangle, here is my right angle, okay? What would be the purple triangle's hypotenuse? A to C, right? Okay? So A to C down here is the hypotenuse, okay? If I draw the altitude from the right angle to the hypotenuse, so it is that segment right there, right? BD, does that make sense? When I do that, I generate two smaller right triangles, correct? And with two smaller right triangles, get more hypotenuses, right? Okay? So in this theorem, when it says hypotenuse, it's talking about the one for the purple triangle. It's talking about the overall one, or the one that you started with. Okay? It says when the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude The length of the altitude. So in this case, the altitude's length would be BD, right? So the length of the altitude is the geometric mean. Well, that means that whatever that distance is, it's going to go there in those proportions. Does that make sense? It's the geometric mean. Now it says it's the geometric mean between the segments of the hypotenuse. Again, the segments of the hypotenuse is this bottom one. Okay? What two segments make up that bottom hypotenuse? Yeah. When we draw that altitude down, it breaks it up into AB It breaks it up to A, B, and BC. So that is what goes in the other two spots.
A couple of afternoon announcements. For those of you that are involved in track conditioning, Coach Bassett has indicated that will take place in the elementary gym from 3:30 to 5 o'clock tonight. And for those of you planning to attend the College Credit Plus meeting tonight, that has been canceled. So please don't show up tonight for the College Credit Plus meeting. It has been rescheduled for February 19th, and I believe guidance might be posting some information to our webpage. So be sure to check that out. Thank you.
So when we draw this segment down, it is the geometric mean between AB and BC. Let's go back real quick and we'll be done. So what I showed you earlier, okay, did this red segment, which was CD, come down here, see, this is the one that's using C and D, right? Okay. Did it create the geometric mean between AD and DB? Does that make sense? All right. So this corollary, it's not necessarily considered a theorem, it's a corollary or a lemma, generates that proportion that we could only find prior by essentially writing down 9 ratios and then deciphering which of those 9 to look at, which 2 of those 9 to look at. So I want to spend quite a few more days on this, and I'll give you one quick example here of what we're going to be doing. Okay, we got a little bit of time yet. They're going to give you pictures like this, and let me get a blank one here. They give me this, and I'm just going to plug in what's provided here in the description. They say RS is 3, QS is 14. They want you to find PS, so I'm just going to call it X. Okay. We prior could only do this if we knew which triangles were similar to one another with those 9 ratios. But right now we can see that this overall triangle PQR, because of that angle right there, is a right triangle. This would be the segment that is the altitude drawn to this being your hypotenuse, right? Okay? So we just learned that the altitude is the geometric mean, so it goes there and there. Does that make sense? Okay. Between the segments of the hypotenuse. So then 3 is going to go there, and 14 is going to go there. Does that make sense? It's pretty easy to solve. X squared is equal to 42. You're going to take square root of both sides, and your answer for X is radical 42. And that's simplified. It doesn't go any smaller than that. Okay? What I told the last class is that when we're doing this, and we could have done this on that question 14 that I gave you on that other worksheet, does this look like a T, what I've highlighted here in the triangle? It's like upside down though, right? Does that make sense? Okay, a capital T. If you can see that in that capital T, you've got like the base of the T, you've got that thing right there, that's the geometric mean, and then you've got the tops of your T, which would be the parts of the hypotenuse. Does that make sense? If you can see that, hopefully maybe it tells you where things go in your proportion. We'll see a lot more examples in the next couple days of this. Okay.